Hi, my name's Will Eastcott. I'm the creator of PlayCanvas, and I'm going to be talking to you today about optimizing HTML5 games based on 10 years of learnings working on the PlayCanvas game engine. So to begin with, I want to just start by explaining a little bit about what PlayCanvas is. It's an open source game engine. It's written in JavaScript. It's based on WebGL, and you also get this visual editor that's like browser-based. It's real-time collaborative. It's built in the cloud. So you can visually build your games in this editor. So PlayCanvas actually powers Snap Games, which is the gaming platform in Snapchat. It's had over 200 million players. There's a large number of games that you can check out at just about any genre, so I would encourage you to check them out. But PlayCanvas isn't just used by Snapchat-based game developers. It's used by game developers the world over to make all sorts of different types of games, from casual games to .io games. It's actually pretty popular for FPS game developers, and you can see several of those represented there. Now, my personal journey in working on game optimization started in the early 2000s, working for a company called Criterion Software on a game engine called Renderware. Now, Renderware was used to power about a third of the games in the sort of PlayStation 2 generation. And day to day, I would be working on this type of hardware. So we're talking a T10000 PlayStation 2 developer kits. And if you wanted to do performance analysis on that kind of hardware, you would struggle. And you would often need to go into Sony's HQ and work on special hardware that was developed by them, very expensive hardware. It was incredibly inconvenient. Fast forward to 2022, and HTML5 game devs are living the dream, right? I mean, we've got incredibly powerful hardware in the palms of our hand, and we've got great tools that are built right into our web browsers. So is optimization still important? Well, spoiler alert, yes, it is. Now, performance optimization, in my view, kind of falls into two main areas. There's load times, and there's also frame rate optimization. And let's start talking about load times. Now, this is something that we don't want our end users to see, loading bars. So why does it matter whether we present our users with loading bars? Well, as it turns out, after 6 seconds of waiting, we tend to lose anything like 40% of our audience who will just bounce, not prepared to wait for the page to load. So when we begin an investigation into load time, what kind of tools do we have available to us that can help us investigate optimizing load times? Well, like I said, built right into the browser, you have some pretty advanced tools. In Chrome DevTools, you have a couple of tabs. You have the networking tab, which shows you what resources my game is loading. And then you have the performance tab that shows how my game is loading those resources. So when you start your investigation, you typically look for the low-hanging fruit. If you look in the bottom left of the browser tab, you'll see the number of requests made by the browser. You'll see the amount of data that's transferred, and you'll see the time it takes to load your game. Now, the first thing that you'll want to do is sort the list of resources based on size, because obviously the bigger the resource, the bigger the opportunity for optimization. You can search for duplicates or redundant resources that your game shouldn't really be loading in the first place. And if we look at the biggest file that's being loaded here into our game, it's a 2.2 megabyte JPEG. So we can ask ourselves, hey, can we downsize these resources? Can we optimize them somehow? Now, as it turns out, in HTML5 games, typically most of the data tends to be texture-based data. And In our example on the previous slide, we had a 2.2 megabyte JPEG. Now, if the browser downloads this file, we need to decompress it into memory. And that is 48 megabytes of data. Then we have to pass it to WebGL to be used as a texture. And a copy of it is made. Plus, we have to generate bitmaps, which is another 64 megabytes of data. So together, that's like 112 megabytes of data just for a single JPEG. Now, if you try to load about 10 of these into a browser tab on mobile, I guarantee you'll crash the tab. So we need some kind of solution around this. Moreover, every JPEG reload, we have to pay like a decode cost. It takes time to actually decompress the data from JPEG to an uncompressed format. And in this case, this 2 megabyte texture takes 160 milliseconds, which is just excessive because it's going to cause the main thread to block and it's going to cause long load times. Luckily, we have hardware texture compression that we can use to load more optimized texture data. So if we take our original 2.2 megabyte JPEG and we crunch that down to some natively supported hardware texture formats like DXT, PVR, and ETC, we find that the sizes are actually larger than the original JPEG. But because the format of this hardware texture compression data is native to the GPU, we can just supply it to the GPU with no decode cost, which is great. Also, the amount of GPU memory used by hardware texture compressed data formats is between 1/5 and 1/10 of the original JPEG. So we're at least sure that we're not going to be crashing the browser tab anymore, but we are paying the cost for having to download large images, and that's a problem. So what can we do? Well, fortunately, there's another texture format called Basis, which is essentially an abstract compression format that is supposed to be transcoded to any of the natively supported formats at runtime, at load time of your game. So if we take that original JPEG and we convert it to a Basis texture, it goes from 2.2 meg down to 1.7, which is great. But also, we get all of the benefits of these native formats. So again, between 1/5 and 1/10 of the original GPU memory that the JPEG occupied. So what does compressing textures to Basis look like in the PlayCanvas editor? Well, it's a very simple operation. You just select the textures that you're looking to compress. You can see we've got 4 2K textures here, which are like 5 megabytes of PNG data. You just say, hey, I want these to be Basis compressed. You import the transcoder, and you hit the compress button, and there you have it. It's very simple. So after texture data, the next biggest contributor to download size in an HTML5 game is often mesh data, at least for 3D games. So let's talk a little bit about mesh optimization. Here we have something called a Stanford Dragon. It's a mesh that's often used in rendering experiments, and we're going to use it in some tests here. Now, you can see it's a very dense mesh. It's got hundreds of thousands of vertices and triangles. Probably not a typical game asset, but it should make some underline some points I'm going to make. So if you were going to start thinking about a format to load this data with, well, I think it's reasonable to start thinking about JSON, because JSON works great with the browser. It's very easy to work with in JavaScript. You can just parse the data into a JavaScript object. So incredibly convenient. Now, it turns out that this Dragon mesh will serialize to 43 megabytes of JSON. That's fairly big, but it will juice it down relatively aggressively down to 12.8 meg. The big problem we have here, though, is that to parse that much JSON takes 1.25 seconds. And also because we're having to throw around quite a large JSON file, there's quite a high peak memory usage of the application. So what can we do? Well, the Kronos group owns an open standard called GLTF, which is essentially designed to be the JPEG of 3D. A large ecosystem has grown up around GLTF, various companies providing tools, such as PlayCanvas, and we now use GLTF as the primary format for the engine. So let's examine what GLTF, how that performs with this particular data. GLB is the binary format of GLTF. So if we save out a GLB file containing this mesh, we find that it's less than half the size of the original JSON file. And when gzip, it's only marginally smaller than the JSON data. That's because JSON is text and it compresses very well. The key thing to notice is that the parse time for the mesh, the GLB file, is just 50 milliseconds, a tiny fraction of the time it takes to parse the JSON, which is pretty incredible. But the reason for this is that the GLTF format stores data in a GPU-ready format. So once it's copied out of the file, you can pass it directly to WebGL with no processing. So this is a huge win for game engines and HTML5 games to ensure they're using GLTF. Also, the peak memory usage is lower because, like I say, we're not throwing around large JSON data sets. We can do even better than this, though. We can compress the GLB file using some technology from Google called Draco. This is an extension of the GLTF specification and allows you to compress the vertex data. So here we can see that the 21 meg GLB can be compressed down to 1.84 megabytes. And you can even gzip that slightly further, down to 1.79 meg. The only slight issue that you must be aware of is that this data needs to be decompressed at load time. So to run the Draco decompressor for this mesh takes 0.4 seconds. But as we did with the basis textures, we can offload that to a web worker thread, and we can then not store the main thread and essentially hide that processing. I've mentioned a few times it's important to use gzip or compression as part of your process to publish your games. It's very critical that your infrastructure, your server, serves your game resources compressed. So to verify that, you should be able to select any resource and look at the content encoding header and check that it's set to either gzip or brotli. Now, how you compress your data to put it on your infrastructure will depend on your backend services provider. The technique will be different per provider, but here there's an example of how you would do it with Google Cloud. You would use gsutil, and you would specify which file types you want to be gzipped. So let's apply some of these techniques to the HTML5 game Swoop. We can see that the original game used JPEGs and JSON for model data. And the original load time was 4.5 seconds total. So just by crunching all of these JPEGs down to basis and re-importing all of the artwork as GLB instead of JSON, we can shave an entire second off the load time. And that represents a few percent of your audience that you've managed to retain by reducing that load time. There are other techniques for improving your load times. One which is actually thinking about your game design. So one of my favorite games of all time is Metroid Prime. And they had an interesting technique where you could move from a large open area to another large open area through a tunnel. And when you're moving through the tunnel, they unload the previous area and start asynchronously loading the next area. When you get to the end of the tunnel, you shoot the door, and as soon as the next area has finished loading, the door will open. And it means that in the entire game, you don't see loading bars and the entire environment seems completely seamless. This technique is used in many PlayCanvas games. So here we have Bitmoji Party, which loads a very minimal set of assets to show that initial menu. It maybe takes 2 seconds for that first initial menu to load and be displayed and be interactive. And while the user is spending those 2 or 3 seconds just deciding what they want to select in terms of an initial gameplay option, we can be streaming the first set of assets in that mini game on the right. And it means that in that particular game, you don't see loading bars. Let's move on to talk about frame rate optimization. Well, why do we care about frame rate these days? Surely smartphones are pretty powerful these days, right? Well, it's interesting if you go and look at some of the benchmarking numbers for phones that are on the market today. So I took the iPhone 13 and the Samsung Galaxy A21s. And the iPhone 13, in terms of CPU benchmarks, outperforms the A21s by like an order of magnitude. This is a huge difference. So it's important that your game can scale from the high end all the way down to some of these more budget devices, as well considering some of the legacy devices that aren't even on the market today. What tools do we have in our arsenal to be able to investigate frame rate? Well, during load time investigation, we looked at the performance tab. The performance tab is very powerful. You can also use it to run a hierarchical profiler for your code. So you can capture a trace over, say, 10 seconds, and you can then drill down into the call stack of your game and identify the hotspots that take up the most CPU percentage, and then focus your efforts there. We also have the timeline view in the performance tab, which allows you to zoom into an individual frame and have a visual representation of where time is spent in that individual frame. So here I can see that my game loop consists of an update and a render. Now, in this case, the render function takes almost 3 times as long to run as the update function. So I'm clearly going to want to focus my efforts there because most of the performance wins can be found there. So to investigate rendering performance, there are many tools available that run as browser extensions. One really great one that I recommend is spectre.js. It allows you to capture a single frame of rendering, and it shows how WebGL is being driven. So you can see individual draw calls being submitted, and you can even drill down and see shader code that's being executed. Perhaps the biggest mistake I see game devs make today is picking the wrong resolution for their game. Now, I picked a couple of devices here to make a point. The iPhone 13 Pro Max actually has 20% fewer physical pixels than the Samsung Galaxy S6, which is a 7-year-old device. Whereas the S6 actually has, obviously, a much weaker GPU in terms of fragment processing. So it wouldn't make sense for you to just like render your game liberally at full device resolution on any device. What you can do is either give the user an option to render at different resolutions, or better yet, you can detect the GPU. You can do that on Android, and you can make a decision about the rendering resolution based on the family of GPU that you've detected. Something else you should consider is limiting the graphical complexity of your game. So on the left, there's a game called Bitmoji Tennis, which is very simplistic. It uses a single emissive map for the environment. There are no dynamic shadows. Everything is baked. There's a single directional light for shadows, well, for lighting the characters. And then on the right, you can see there's a much more complex demo, graphically speaking. It's a technical demo that the PlayCanvas team built, which uses physical shading, shadow mapping, image-based lighting, and other effects as well. And the complexity of the shaders of the game on the left is far simpler, and therefore it puts less strain on the GPU and you're able to render at a higher frame rate. I also recommend that you be very careful about the number of draw calls that your game makes. Now, a draw call is essentially submitting a graphical primitive to the GPU with some render state. Every draw call will have an overhead in terms of CPU and GPU cost. And a typical HTML5 game might render between, say, 100 and 200 draw calls if you want to target some of these low-end devices. So one technique for optimizing draw calls is atlasing textures. So for this environment that you see rendered there are several materials. There's wooden planks on the floor, there's wallpaper on the walls, etc. Now, these textures are atlased into a set of textures, and this means that draw calls can be combined together. Another technique is batching, where we have an environment that's rendered using 7 distinct models. And some of these models are rendered multiple times. Like you can see, for example, some of the buildings are duplicated, the cacti are duplicated. And when we render this scene normally, this is kind of the way the scene is built up. You can see there's like an individual draw call per object. But if we use batching, we can combine similar models into like combined draw calls, if you like. And this means that we can render the entire scene in just 6 draw calls instead of the original 50. So almost an order of magnitude reduction, which pretty much maps to an order of magnitude lower processing on the CPU and the GPU in terms of, well, I mean, lower on the CPU and on the GPU, it's a lower overhead because there's fewer draw calls. So I'm going to leave you with 3 key pieces of advice here. Do not leave optimization considerations until the end of your development process. Also, design your game with performance in mind right from the very beginning. And lastly, select what your baseline device is and test on that device early and throughout your development cycle. That's it for this talk. Thank you for listening.